last lecture, of course, we had started with the discussion of the doubts or questions from calculus, but having done that, we had also got into kinematics of motion along a straight line. So let me just review and recap the things that we discussed related to that in the last session. So we had seen the general relationship between velocity, displacement, and acceleration from a one-dimensional kinematics perspective, motion along a straight line. And then we had gone on to see the special case of uniformly accelerated motion. And we had seen the derivation of the three equations, the three standard equations of motion along a straight line with uniform acceleration, that v equal to u plus at, and those three equations in general. We had seen the derivation of those. Just a second. Yeah, so we had seen the derivation of those on the basis of integral calculus. So let's take a quick recap at that concept and begin. So uniformly accelerated one-dimensional motion or motion along a straight line. So we had seen that acceleration is constant or uniform. That's one and the same thing. So from this, we basically have the relation that instantaneous rate of change of velocity is a constant. So by cross multiplying the dt and integrating both the sides, it's seen that at t equal to 0, if the initial velocity is u, and at some time t, the instantaneous velocity is v. From this integration, we got the relation that v is equal to u plus at, which was our first equation, which gives us the instantaneous velocity as a function of time t, where of course u is the initial velocity and a is the acceleration, which is of course uniform. Then on integrating this relation, we saw we got displacement as a function of time. So you got the second relation, s is equal to ut plus half at square, which is displacement as a function of time. So you can quickly review these two integrations. We have done this in the previous lectures, so you don't need to write down all the steps in detail, but you can just review, and in case of any doubt or in case something is not clear in this, you can just clarify that with me. Then we'll discuss further. Okay, so then moving ahead, the third equation we had seen comes from using chain rule in the relationship between instantaneous velocity and acceleration. So acceleration, which we define as dv by dt, can also be defined as dv by ds into ds by dt, where ds by dt is of course the instantaneous velocity. So acceleration is v dv by ds. So if acceleration is uniform, that means v dv by ds, which is equal to a, is constant. So integrating this relation from initial velocity equal to u when displacement was 0 to instantaneous velocity v when the displacement is s, we get the relation that take the constant outside. So we get v square by 2 from u to v is equal to, on the other side, as from 0 to s. So I'm just doing this one in a little bit more detail because we have done this towards the end of the last lecture. So may not have paid attention to all the steps. From this relation we get, so this is the relationship between instantaneous velocity and displacement s, which is the third equation almost. So So these are the derivations of these equations based on calculus or based on definite integration. In case of any doubts, please let me know. It's very important that you understand how these equations evolved from application of calculus. And of course, it's very important to learn how to apply these equations in problem solving, which we will spend most of today's lecture doing. So let's start with one example. So a particle moving along a straight line with uniform acceleration. It starts at t equal to 0 and at an instant t equal to 2 seconds, its velocity is 70 meters per second and its displacement is 120 meters. Calculate its acceleration, its initial velocity, and its velocity at an instant when its displacement is equal to, just give me a moment, 280 meters. Okay. So this is like the first level of problem, which is, I mean, basically you can say almost your board level of problem, where you have to do direct application of the formulae, which formulae the three standard equations, which is for uniformly accelerated 1D motion. So you have to do direct application of those three equations or formulae to find out the unknown quantity over here. Just give this a try. Try to correlate from the language of the question what information is given to us and how we can fit the information given in the appropriate equations so that we can find out the unknown quantities. What are the unknown quantities? The initial velocity and the acceleration. Once we know V and A, then we can easily answer the third part or any other part for that matter. Okay. Nobody sent the answer yet. People, did you
2
try out?
minutes.
2 minutes? Okay.
Sir,
Yes, yes.
in the first statement, sir, acceleration will be 0, no?
No, beta, because it's saying that it is moving with uniform acceleration. No?
Yes,
Okay.
sir. Okay.
And another thing you can see na, that if it was moving with uniform velocity, मतलब अगर acceleration 0 होता, then velocity would have been uniform, na, beta 70. Then in 2 seconds, how much the displacement would have been? It would have been 140 meters. So the fact that the displacement is less than that, it's only 120 meters. That means it's not moving uniformly at 70. You understanding the point? No?
Yes, sir.
Suppose I had given the displacement as 140. Then when you put in the equation, your value of A would have come out to be 0. Yeah, it would have been justified. कि चलो acceleration बोला है, but actually है नहीं, according to the data of the question. But here you will see the data of the question shows you that actually there is acceleration.
Yes, sir.
So you have to
Just give
substitute
2 minutes.
these two information in the equations. Okay, this
Yes.
has to be substituted that at t equal to 2 seconds, okay, b is equal to 70 meters per second and s is equal to 120 meters per meters. Okay, so from this, what is your unknown? U is unknown, a is unknown. So just try to substitute this in the equation and solve.
Yes, sir.
Yes, Tejas, your answer is correct. Anybody else has got the value of acceleration? Very good, Aman, but there should be no minus 50. Its initial velocity is positive only.
No, it's no, sir. It's a dash actually. It's
Acha,
not.
acha, dash only. No, okay, okay,
Yeah.
yeah. Okay, your answer is correct. Good. Now just work out the third part. So I'm just explaining to the others how you will substitute. Okay, so you will use the equation v equal to u plus at. Then you can use the equation s is equal to ut plus half at square. And if required, we can use this equation also. But in this case, we'll end up using just this. So 70 is equal to u plus 2a. And the second equation, you substitute 120 is equal to 2u plus 2a. So solve these two equations and you will get the value of acceleration and you will get the value of initial velocity. Yes, Tejas, your answer is correct.
So,
Yes.
so we could also go by the third equation and we could just substitute the value of u from the first equation. So is that also possible?
Yes, that also you can do. What you can do is you can see what you can do is from the first equation, you calculate the value of or you substitute in the third equation. So any combination of these two will do. Okay, so in the third equation, 70 square is equal to u square plus 2 a into 120. So you can do this also.
This part will be more lengthy, no? If you use first and third.
That's what I'm saying because it's a quadratic equation in u, so it will become a little more lengthy. So it is better that you solve these two. If you, for example, just subtract equation 1 minus 2 or whatever 2 minus 1, you will get 50 is equal to u directly first thing, and then substitute this in equation 1. So you get a as 10. That's it. So that's your answer. So u is 50 meters per second. A is equal to 10 meters per second square. The proper units. Okay. And then for the third part of the question, you use that equation, the third equation. So this is the first part. This is the second part. Now for the third part, what you can do is you can use equation 3. So v square is equal to u square plus 2 into a into s when the displacement is 2a. So you can see that v will be square root of 50 square plus this will become how much? 5600. So you can take 25 plus 56. It's 10 root 81. So you can see it is 90. So this is how you can do the third part in one equation. Otherwise, you can also use equation 1 and 2, but this will be more efficient.
So,
Yes.
so we could say that like second substep we found it first and then acceleration, right? Like
Yes.
first we u and then.
See, two informations are given to us, na? That at t equal to 2 seconds, velocity kitna hai, that's given, and displacement kitna hai, that is given. So using these two informations, we are generating two equations. But actually, I have shown you three equations, but two equations is enough. So I've used only one.
Yes, sir. Yes.
And then instead of simultaneously solving these equations for the unknown
Yes.
quantities. Okay, this is done now.
Yes, sir.
Yes.
Sir, I understood the first and second. Could you please explain the third part?
Third part mein dekho what we have to do. We have to find the velocity when the displacement is 280 meters. So at some point of time, the displacement is 280 meters. So then at that point of time, what is the velocity? what is the velocity at the time when the displacement is 280 meters. So there are two ways of doing this. One is we could find the time. So for that, use the equation that 280 s is equal to ut, that is 50t plus half at square. So that will become 5t square. So from this, solve for time and then use the equation v equal to u plus at. So velocity at that moment would be 50 plus 10t. So substitute that time over here and then we could find the velocity. But that's a two-step process, no? It's lengthy. So instead what we are doing is we are directly solving. So we are saying that, okay, this is the relationship between v and s. V square is equal to u square plus 2as. So in this we substitute the value of s as 280 meters to find out what is the velocity at that moment. Is it clear now?
Understood, sir.
Okay. So you can go with this method also, but this will be lengthy because you'll have to solve a quadratic equation to find time, then substitute that time in the first equation, and then that will give you the velocity. Okay. But this is the faster method. Okay. Just for reference, you can actually solve this. You can see this is t square plus 10t minus 56 is equal to 0. Yeah. So this will give you t equal to 4 as one root and minus of 16 as the other. Okay, so we'll take t equal to 4 and reject this. So we'll substitute this here. So we'll get the velocity as 50 plus 10 into 4. But it's more lengthy. So the direct method is better because we have to just find the velocity at the time when the displacement is 280. So we just use the third equation, which is the relationship between v and s. This third equation. So many a time in this type of problem solving, you will see that you have options of using different combination of equations. And if you take one option, it might take longer to solve the question. If you take the other option, it might be faster. So end of the day, every option will give you the answer. That is not the problem. Okay? And you can practice this out by various different options to gradually understand that, you know, when to use which equation so that you come to the fastest answer. I mean, you are able to solve the question fastest. So it's just a matter of practice, nothing else. Okay, now let's move on to understanding graphs, velocity time and displacement time graphs for this situation of uniformly accelerated 1D motion. Okay. So why these graphs are important is because they'll help us understand two important cases, okay, of this. The first case is when u is positive and acceleration is also positive at t equal to 0. That means the acceleration causes or is in the same direction as the initial velocity. So velocity increases with time straight away from t equal to 0. That's so let's understand this sort of a graph with an example case. Suppose we had an example where our initial velocity was, I'm writing with sign because it's showing me that it's along the positive direction, and a uniform acceleration. So uniform acceleration of, let's say, plus 2 meters per second square. So now let us understand how the displacement and velocity will vary with time. So v will be equal to u plus at. So velocity as a function of time will be, as you can see, 20 plus 2t. So what kind of graph this will be? This will be a linear or straight line graph V versus T will be a linear or straight line graph with a slope of +2. So that graph will look like this. Plot velocity in meters per second versus time in seconds. We can see that at t equal to 0, the value of velocity would have been 20 meters per second. But from there onwards, it's increasing. So that's why the slope is positive. It's increasing linearly because it's a linear equation, b equal to u plus at. It's a linear equation. So velocity as a function of time, this has a slope equal to the acceleration, which is +2. So for example, after,
Sir,
yes,
sir, how did you get the slope +2?
by comparing with the equation of straight line, beta, okay, y equal to mx plus c.
Yes, sir.
So यहाँ पे y की जगह क्या है, v है, and x की
Sir,
जगह
V.
क्या है.
Sir, T.
So time का coefficient क्या है, it is +2.
No, yes, sir. Yes, understood.
See the slope m is equal to +2, and the y-intercept,
It's 20.
or c, that is 20. So that is why my graph is looking like this, that it's cutting the y-axis. In this case, the velocity axis at 20 plus 20, and the slope is 2. So that means every 1 second, the velocity is increasing by 2 meters per second square. So for example, after 5 seconds, it would have increased by a factor of 10. So the velocity would have become 30 like this. So you can see that this slope, look at this slope, is delta v by delta t slope, which is your tan theta. Is +2. Okay, so just I'll take you back to the beginning of this. Okay, just make a note of this example. Okay, so first the heading, that we are looking at velocity versus time and displacement versus time graphs. So we'll also look at the S versus T graph for this example. But in general, what we are doing is we are looking at VT and ST graphs. And the first case over here is we are looking at is when U and A are both positive. That means the acceleration is in the same direction as the initial velocity. So the velocity increases with time straight away from t equal to 0. And as a numerical example, we've taken this one. So the graph of V versus T is looking like a linear graph with a positive slope because acceleration is positive. Positive slope basically means that velocity is increasing with time straight away. Okay, so make a note of this. Yes, yes.
So actually, I had lost my connection, so I didn't understand this part, sir. So after v equals to 20 plus 2t, sir, how did you get?
I explained the whole part again. You substitute u and a, so you are getting the equation b equal to 20 plus 2t. Na? So now it's just plotting that graph.
But sir, how did you get the slope as +2?
वही तो देखो साइड में लिखा हुआ है ना, y equal to mx plus c में स्लोप क्या होता है, x का कोफिशिएंट. So यहाँ पे x एक्सिस पे क्या है, टाइम है ना. So what
Yes,
is the
sir.
coefficient? It's 2 na. So the slope
Yes,
is 2.
sir.
Okay. Moreover, you compare that equation, you know that what is slope of v versus t. It is delta v by delta t. That is nothing but acceleration. So acceleration is +2.
Okay, sir. Understood. Thank you, sir.
Okay, next we will look at the displacement time graph.
Please wait 1 second.
Okay. Okay, next if we look at the displacement versus time relation. So here we can see S will be equal to 20t plus t square, because the value of u was 20 and the value of a was 2 meters per second square. So now you can see that this is a S is what we call a quadratic function of time. Okay. And its graph will be what we call a parabolic curve. The shape of the graph is called a parabola. It is called a parabolic curve shape graph. That will be a S versus T graph. So that will look like this now. So S in meters, let's say, versus T in seconds. So if you just take some values of it, you'll understand why the graph will be the way I'm drawing it. It will be a curve which goes like this. The slope of the curve is increasing because the slope is nothing but the velocity. The slope of tangent ds by dt equals to velocity, instantaneous velocity. So here, because this is increasing, so you can, if you compare the tangent at one point, you can see that after some time, if you draw a tangent, the graph's shape is such, the curvature is such that the tangent slope has increased because the velocity is increasing. So the slope increases with time. That is why the displacement looks like this. So for example, you can see that displacement at 1 second, for example, is 21 meters. But the displacement at, let's say, 2 seconds is how much now? 44 meters. The displacement at 3 seconds, for example. I'm not drawing the graph to scale, but just. So the displacement at 3 seconds would have become 60 plus 9. So 69. So you can see that it's increasing in a non-linear fashion. The values are such that it's a curvature. And because it's a quadratic function, that sort of curvature is called a parabola mathematically. So it's a parabolic curve, the displacement versus time. And the curvature is such that the slope is increasing because the instantaneous velocity is increasing. Okay, so this is the graph, or rather these are the graphs of V versus T and S versus T in the situation where U and A are positive. That is our first case. Now we look at the second case after this where A is negative. We see that there's a difference in how the graphs will reflect that information.
Done, sir.
Okay.
1 minute.
Yeah, sure. Write
1
this down.
minute.
Rajavardhan, there's somebody called Rajavardhan here. Can you just unmute yourself? Yeah,
Oh, sir, that's me, Harshvardhan. I
Harshvardhan.
forgot.
Okay, okay. Next time, na, just log in with your name and roll number, na, everybody, please. So just
Yes.
let's. Okay,
Yes.
Harshvardhan, beta, which center you are in?
Yes, sir. What?
Which center are you admission? Is your admission in?
Sir, Khargar.
Khargar, no? Okay, okay, okay. Okay, so people, you finished with this graph, all of you?
Yes, sir.
Okay. Now let's see the other situation where, so
Sir,
either,
I've
you know,
the name.
beta, tell.
Sir, I've renamed myself.
Okay, okay, okay. Thanks, thanks. Okay. Actually, you know, there's a person who takes the attendance, no? So it gets confusing sometimes if you don't.
Yes, sir. I know. I forgot. My brother also does class in this phone only. That's why.
Oh, okay, okay, no problem. Okay, now, so see, since you're talking about one-dimensional motion or motion along a straight line, so there are only two possibilities that either U and A are in the same direction. Okay, so that would be a situation something like this. Physically, how that situation would be. That suppose, you know, we have an object which is already traveling along this direction at t equal to 0. It has an initial velocity like this, but we start pushing it like this with some force. So its acceleration is in this direction. So what will happen is velocity will start increasing with time. Okay. So this velocity v would be greater than u because a is in the same direction. Acceleration comes from force. Okay, so this would be the if the a is uniform, then this graph of v versus t would look like this kind of a straight line that we discussed. Okay, but now there's also a second possibility that the force. Sorry, this is the first case. Yeah. Now there's also a second possibility that the force is actually acting in the opposite direction. So in that case, what will happen? The velocity will initially decrease. Later, it might increase again. So we'll come to that also. Okay. But at least initially, what will happen if the force is acting from the opposite direction? So the acceleration vector is in the opposite direction. So at t equal to 0, initial velocity is like this. But let's say I start applying a force in this direction. So now what happens? The acceleration is negative compared to the initial velocity. So this is the case where A is opposite to U. So in this case, if this is, we are assuming this is a uniform acceleration, then because my A is a negative quantity compared to U, the velocity versus time graph, at least initially it will look like this. Eventually it might become 0 and then negative, but initially the velocity will be decreasing. So this is the second case possible, and there's no third case. Okay, I mean, you can of course swap the directions, but important thing is either U and A are in the same direction or they are in opposite directions. There's nothing else that's possible. Now there might be combinations like this that U is positive, A is negative, U is negative, A is positive. All those things are there. But importantly, what is happening? Either they are in parallel to each other, they're in the same direction, or they are opposite to each other. That means they're at 180 degrees to each other. So in that sense, there are only two cases which are possible. Okay, so now we will discuss the graph for the second case. So this is our case 2, where we'll take U as a positive quantity and A as a negative quantity because they are opposite in direction. So let's take an example where our initial velocity is again 20 meters per second, but this time our acceleration is -4 meters per second square. So some constant force is acting in such a way in the opposite direction that it's creating an acceleration of magnitude 4 meters per second square, but the direction is opposite to the initial velocity. So from this information now, we can say that V equal to U plus AT will give us the relation that V is equal to 20 minus 40. So now if you see this, this is that kind of graph. This is time, this is V, but M is minus 4 over here. So it's having a negative slope. And the y-intercept is equal to 20. So it will be a linear graph with a negative slope.
Now, what is linear graph?
Linear is straight line, beta. Any equation of the type y is equal to mx plus c is called a linear equation, and its graph is called the linear graph or a straight line graph. Whereas equation of the type ax square plus bx plus c is called a quadratic equation, and its graph is called a parabolic graph. Let's take a look at the graph of velocity versus time. So of course, time can't be negative. Time will start from t equal to 0. But velocity can become negative because if this acceleration continues for long enough time, then it will make the velocity become opposite in direction. So here we can see that it's starting with a velocity of 20 meters per second. But for example, after let's say 2 seconds, how much the velocity is becoming? It's becoming 12. Okay. Then you can see after 4 seconds, the velocity is only 4. Which means that exactly at t equal to 5 seconds, what is happening? The velocity is 0. So from this, you can see that v equal to 20 minus 40 means that at t equal to 5 seconds, the instantaneous velocity is 0. And for time greater than 5 seconds, the instantaneous velocity is negative. Whereas for time less than 5 seconds, the instantaneous velocity is positive. So for example, at 6 seconds, you can see that the instantaneous velocity would have become minus 4. So minus 4 means basically what? That the direction of motion has reversed.
Sir,
Yes.
in the above one example also, the force is opposite, no? So the acceleration is opposite, no?
Yes. They
Here
are both
also.
the same. This is case 2 only, sorry. This is an example of case 2. Okay. The same.
Okay, sir.
So actually, you can just write it like this. This is only case 2. Okay, so write down up to the graph of velocity versus time, and then also try to figure out yourself how the graph of displacement versus time will look like. So first write the equation for displacement versus time as using s equal to ut plus half at square. Substitute the values and write the equation, and then try to figure out how the graph should look, how it should be different from the earlier example that we have taken.
Sir,
Okay, so let's look at the acceleration versus time graph, how it looks different. Yes, acceleration is retarded, but it is up to a certain time. So I'll explain that also. See what is happening now, that you'll understand this from the velocity time graph, Mani. Okay, you can see that in the above case, u is equal to plus 20 and a is equal to minus 4 meters per second square. So from t equal to 0 to 5 seconds, okay, the velocity is decreasing from 20 meters per second to 0. So this is the situation where it decelerates. But from t equal to 5 seconds onwards, velocity is negative such that the magnitude of velocity, that is speed, is increasing. So again, it is accelerating because the speed is increasing. So for example, you can see that t equal to 6 seconds, the velocity is minus 4. T equal to 8 seconds, for example, if you calculate, the velocity would have become minus 12. T equal to 10 seconds, if you calculate, the velocity has become minus 20 meters per second. So the speed is increasing. So again, it is accelerating actually. This part of the motion, again, it is accelerating. So it's a combination of deceleration initially, and if that negative acceleration continues for enough time, that actually ends up reversing its direction and coming backwards, then again it starts accelerating. So it's like, if you try, if you want to understand this, like as if it's happening on a surface visually, like on a time scale. So t equal to 0, starting with a velocity of 20 meters per second. Now from here onwards, it's decelerating. You can see that at 1 second, it's moved forward, but its velocity is reduced to 16 meters per second. At 2 seconds, its velocity is reduced to 12 meters per second. At 3 seconds, its velocity is further reduced to 8 meters per second. And like this, at t equal to 5 seconds, it has stopped. Momentarily it has stopped because its velocity is 0. But then after that, what happens? It starts returning backwards. So for example, it now has a velocity of minus 4 meters per second at t equal to 6 seconds.
Yes, sir, got it, sir.
So you can see something like this is happening. Its velocity will become like minus 20 meters per second at the time the time is, or let's say this is this one. It is say minus 60 meters per second because the time here is 9 seconds, like this. So the direction of motion is reversed. And once it is reversed, that negative acceleration will actually cause its speed to increase. So from here to here, you can see the speed is increased.
Yes, sir, I understood, sir.
So this is an important aspect to understand.
Sir,
Yes.
we have to draw this.
Not necessarily, just understand it. It's important. I'm sending you the notes anyway, so you don't have to write everything in detail during the lecture. What you should do is the questions that I ask you to solve, that you should do very carefully, and the derivations like we do using integration and all that, when I ask you to write, you should write them carefully because I want you to do the steps yourself first. The rest, I'm sending you the notes so you can make fair copy of the notes later when you're revising if you want. So Need not always write everything.
Also, after a point, displacement will go negative as well, right? Because
Yes,
it's
very
going in
good.
the
So
opposite direction.
So if it continues with this negative acceleration, so what will actually happen is that not only its direction of motion is reversed, but like you correctly said, it will retrace its path. But however much it had gone in the forward direction, it will come back in that much only, and it's come back to where it started. So it will be over here after some time, at the starting position. And after that time, now what will happen? If it further continues having that negative acceleration, it will actually have gone in the opposite direction. So its displacement would have become negative now. So that is what our displacement time graph will reveal next. Okay. So let's come to the displacement versus time. So U was plus 20 meters per second and acceleration was minus 4. So using the relation that S is equal to UT plus half AT square, I'll see that this is a different kind of parabola because the coefficient of T square is going to be negative now. Is going to be minus 2T square like this. So you can see that this is such that 20T minus correction UT plus half AT square, but E is minus 4. So like this. So you can see that if you factorize this, you can take 2T common. So you have 10 minus T. So you can see that displacement is becoming 0 at T equal to 10 seconds also. Of course, displacement is 0 at T equal to 0. And also you will see that displacement becomes negative for T greater than 10 seconds. So this is like what we were just discussing when you said, okay, that displacement becomes negative. Matlab kya hua? It's actually gone past the starting point and now it is behind, or it's on the negative side of our axis from where it had started. So if we are plotting displacement versus time, you will see here that the shape of the graph will be like this. First, the displacement is increasing, and then it starts coming back to where it started from. And this problem is showing us that that happens when it comes back to where it started from. That happens exactly at 10 seconds. After that, the displacement is negative. Also, it reaches a maximum value at 5 seconds. Because at the time, so you can see from here, at t equal to 5 seconds, v, which is ds by dt, is equal to 0. So that means s has the local maximum. Whereas from here, you can see that this also we use that s is 0 again at t equal to 10 seconds. Once I'll just check what you've written. Yes, very good. That was correct. Sorry, I missed your message. Now I've gone through it. That's 100% correct. That S increases up till 5 seconds, but the moment S slowly starts decreasing after t equal to 5 seconds. And now one more thing we have seen, that after 5 seconds S starts decreasing such that S actually becomes 0 at 10 seconds. And after 10 seconds, if the motion even continues, then it actually becomes negative because the object has gone past where it started from. Now it's traveling along the negative side with increasing displacement along the negative side.
Yes, sir.
It's called local maxima because at that point the slope is 0. No? Slope of the tangent is 0. So within a local neighborhood of points, it is the maximum. That's why it is called local maximum, because it is always possible to have a graph which has more number of maximas. Okay? So it may not be the overall maximum. So going back to when we discussed in functions and in calculus, differential calculus applications, local maxima and minima concept. Why we call it local maxima and minima? Because any function y equal to fx can have any shape of graph. It can have a graph like this, for example. So then this point, it has a peak, so it is a maxima, but it's not the overall peak, because there are other points where the value is more. So it is called a local maxima. Similarly, this point is called a local minima because there are other points which are lower than that, but within a local neighborhood, that point has a dip. So it is called a local minima. So that's how the term local maxima and local minima came. So hope this point is clear, Vedant. I mean, it's just a matter of nomenclature why we call it local maxima and minima instead of just calling it maxima and minima. But that is the logic for it. Okay. So anyhow, hope this is clear. Okay, so related to this, now we will solve a quick numerical part. Yes, that's also correct, Vedant. In this particular graph, it is going to continuously decrease after 10 seconds. You will see that if you were to, like, when you differentiate this, now you get the velocity versus time relation. So that velocity versus time relation was what? It was 20 minus 40. No? So velocity is not becoming zero ever again. So that means there is no other point where there's local maxima or minima. There's only one point. So that's why it cannot have any other maximas, or for that matter, any other minimas. Okay, it has only one turning point, which is t equal to 5 seconds. That is the instant when ds by dt is 0 or v is 0.
So can you scroll up?
Yeah. Now in the same problem, we will just solve one more interesting thing. Okay. Just a second, let me minimize this a little bit. Now that we have found the we've drawn the displacement time graph. Now one more thing we'll do here. Find the distance traveled. And the displacement, both the things. From 0 to 4 seconds, 0 to 6 seconds, and 4 to 6 seconds. For these separate intervals, we need to calculate both the things, the distance traveled as well as the displacement. Now, you have to be a little careful here because you understand from the graph that distance and displacement need not be the same thing here because the direction is switching in between. So you have to be careful how you will interpret distance and how it will be different from displacement, if at all that's the case.
Sir,
Yes.
sir, can you explain that how the s equals to 0 and t equals to 10 second came? Sir, I lost my connection at that time.
It's written on the side. See, I factorized this. That 20t minus 2t square is factorized and written over there. So s equal to 0. When you substitute, now you can see it happens at t equal to 0. Just solve for the condition s equal to 0. You will get the root of the quadratic equation as 10 seconds. One of the roots, that is. One
Okay,
root,
sir.
10 seconds. Understood? No?
Okay, sir.
Okay, so from this we can understand one thing, that from t equal to 0 to 5 seconds, direction of motion is along positive axis. Okay, and from t equal to 5 seconds onwards, the direction of motion is along negative axis. Yes, very good, Vedant. That is correct. So that is why when it comes to the A part, 0 to 4 seconds, displacement will be the same thing as distance. And that will be from this equation. This was the equation. Acceleration was 4, right? Oh, sorry, minus. My mistake. Acceleration was negative, so this will be minus sign here. So that is 80 minus 32. So it will be 48 meters. Okay. Or we can actually say that the displacement with the correct sign and all is plus 48 meters, and distance doesn't come with sign because it doesn't have any direction, is 48 meters. But the second part, 0 to 6 seconds, in that the displacement and distance will not be the same. Okay. The distance will be displacement from 0 to 5 seconds plus magnitude of displacement from 5 to 6 seconds. So from this equation, you can see that at t equal to 5 seconds, the displacement is how much? 100 minus 50. So that's 50. At t equal to 6 seconds, you can see that displacement is 48 meters. So this shows you that the displacement from 4 to 6 seconds is 0, because so what you're understanding is that from 5 to 6 seconds, the displacement is actually minus 2 meters. So that is why the total displacement from 0 to 6 seconds is plus 48 meters. But this is actually 50 meters plus mod of minus 2. So it is 52 meters. This is the distance traveled, not the displacement from 0 to 6 seconds.
So,
Yes.
so can you explain again what did you do for 5 to 6 seconds for the distance?
Okay, so see what is happening. What is the displacement at 6 seconds? At 6 seconds, the displacement is plus 48 meters. Whereas what is the displacement at 5 seconds? It is plus 50 meters. So now just visualize what is happening. If it started from here at t equal to 0, at t equal to 5 seconds, it is over here. It is at a displacement of 50 meters from here. But then it's coming back, and at 6 seconds where it is reaching. It's reaching here now at 48 meters. So between 5 and 6 seconds, what is the displacement? Understood? It's minus 2 meters.
Yes, sir.
So that's how we got this, that the displacement between 5 and 6 seconds is actually minus 2. So the distance traveled from 5 to 6 seconds is 2 meters, but backwards. So what is happening in that whole interval from 0 to 6 seconds? 0 to 5 seconds, he is going 50 meters forward. And then from 5th second to 6th second, he's going 2 meters backwards.
2 meters.
So his net displacement is 48, but the total distance traveled is how much? 52.
Okay,
so
like it is negative, but in distance, like since
in
negative is
distance,
not
the length
considered,
of-
so 52.
Yeah, correct. Distance is the length of the path. So the total path length is becoming 50. Okay.
Yes, sir. Yes, sir.
Now similarly, you will see that for this part from t equal to 4 to 6 seconds, what is happening? The distance traveled, it will be the magnitude of displacement 4 to 5 plus the magnitude of displacement from 5 to 6. Now at 4, what was the position? We had seen it was plus 48. At 5, what is the position? It was plus 50. And at 6, the position is again plus 48. So here to here, the displacement is plus 2. But here to here, the displacement is minus 2. So it is a sum of 2 mod of minus 2 is 4 meters. So the distance that is traveling between 4 to 6 seconds is 4 meters, even though the displacement is 0. That is 0. All right, so this is also clear. Okay, so people hope this part is clear to all of you. Now we will apply these kind of equations in a special type of motion which is called vertical motion under gravity, where the acceleration is the value of small g or acceleration due to gravity. So vertical motion under gravity the first case we'll see here is free fall. That is, you drop an object from a certain height and it's moving under the action of gravity. So its acceleration is the value small g, acceleration due to gravity. So let's say from a certain height above the ground level at t equal to 0, an object is dropped. From a certain height h. So what will happen is that as it falls because of gravity, at any instant of time t, its velocity v and its displacement s can be calculated. So here what we will do is we will take the axis, in this case you can take it as y-axis, downwards. Take a y-axis downwards like this. So initial velocity is 0, but our acceleration will be plus g, where g is the acceleration due to gravity. The Earth's gravitational field. Okay, so that is equal to 9.8 meters per second square, or sometimes we take approximate value as 10 meters per second square. But this will be written with a plus sign over here because we have taken the y-axis as downwards. So therefore we can see that at some time t, the velocity, which is u plus at, here the velocity will become g into t. The displacement, which is ut plus half at square, here the displacement will become half gt square as a function of time. And similarly, v square is equal to u square plus 2as. So here v square will become
2gh.
because u is 0. So these are the three important equations. So now let's say that after some time it hits the ground. So that time is, let's say, capital T. So we can calculate the value of the impact speed with which it hits the ground, vi, and the time. So now if it is dropped from rest, it hits the ground h below at t equal to capital T and with speed pi, impact speed. So we also want to find capital T and impact speed. So you can see that in equation 2, s is equal to h at t equal to capital T. So h is equal to half gt square. So the time it takes for it to hit the ground is this. And from equation 3, v impact will become square root of 2gh, because the displacement is equal to h when v is equal to the impact speed. So that vi stands there for the impact speed. Yeah, Vedant, u is 0 over here, but yeah, the motion immediately starts in the downward direction because of that acceleration. So we are taking the downward direction as positive. We can take the upward direction as positive also, but that will give us a negative velocity and a negative displacement after time t, and that will not be so convenient. Though we can solve the equations in that way also, but logically it makes sense. Whatever the direction in which the motion is starting off, that should be taken as a positive axis. Hence,
have to find T and VI, right?
Sorry.
The question for VI and what do you have to find in the second one?
Yeah, so we have to solve the value of capital T and the value of impact speed. So that is coming from these two formulae. Understood? No? So for example, impact
Wait a
speed. It is the speed of impact at the ground below.
Sir, could you scroll up for a second?
Okay, so finish writing this down and then we'll just do a numerical example of this. So suppose a ball is dropped from a height of 20 meters above ground. Take G as 10 meters per second square. Now it is dropped at a height of this much above ground at t equal to 0. So you have to find the time taken to hit the ground below. The impact speed. We have to also find the displacement at t equal to 1 second. And we have to also find the velocity when s is equal to 15 meters. What is the velocity at the instant when the displacement is 15 meters? Okay, so you will be using these equations and these concepts above to solve this numerical problem. Take the value of g as 10 meters per second square and it's dropped from a height of 20 meters above the ground. So just calculate this fast. Okay, so very good. Lot of you have sent me the correct answers. So time taken to hit the ground, you can see, you can calculate directly by the formula square root of 2h by g, or you can understand that s in general is half gt square. So s becomes h when time becomes capital T. So from this, time is 2 seconds. Now from that you can see that the impact speed you can calculate by two ways. I can either do this, so it is 10 into 2 or 20 seconds, because this is when it hits the ground. Okay, so this is the impact speed. Or you can also use this, that 2gh, 20 meters per second. So the impact speed same. Now third part, you can see that displacement as a function of time is half gt square or 5t square. So displacement at t equal to 1 second is 5 meters. We should understand that it is 5 meters downwards because it's in free fall. And the fourth part, v is equal to this equation we can use. So this is the speed when s is equal to 15 meters. Incidentally, s is equal to 15 meters is when it's 5 meters above the ground. Okay, so very good. People have got this correct. Vansh, Avi, Arushi.
So is kinematics coming this major test?
Yes, up to this part, beta. Uniformly accelerated straight line motion. This part is coming.
Okay.
So this gravity part is coming.
As an application, yeah. Like, you know.
So sir, these type of sums will come, no?
Only like vertical motion, not projectile motion, because that we haven't studied yet. I mean, we have done a bit in the board lecture, but not for the IIT lectures.
So, sir, till now, whatever you have taught, that much will come.
Yes. Actually, little less than that. Today's lecture, the type of difficulty level of questions, that same difficulty level will not come. So you can actually take it like the previous lecture, or you can study a little bit ahead beyond the test. So that's today's lecture's problems also.
Okay, sir.
Okay, now the second case we'll wind up with here today is that when we vertically project from the ground. That means project means throw something. So when we throw something vertically upward from the ground level. So this is also a case of that, you know, it will decelerate as it goes up, and then it will reach the highest point and then start coming down. So as it comes down, it starts to accelerate. So it's that type of motion that we were discussing earlier today in terms of graph and all that. So let's say we throw something upwards with a velocity u at time t equal to 0. So what we'll observe is that as it's going up, after some time, if it reaches, let's say here, with a velocity v upwards, you can see v will be less than v, and it will continue going up. But at some instant, because it's decelerating, its velocity will become 0. So when it reaches this point where the velocity has become 0, the displacement has become what we call the maximum height. So it's not going to go further. And from there onwards, it's going to start coming down. It will even cross this point at some point of time, and then eventually it will come and hit the ground. So when it hits the ground, let's say its impact speed is again vi, and the total time is capital T. So we can calculate all these things, like the time it takes to come back to the ground, and the impact speed, and the maximum height, and all that by using this. Okay. Now in this case, what we do is, since it's starting upwards, what we do is we take our y-axis upwards. So because we take our y-axis upwards, so what we'll do is we'll write the initial velocity with the plus sign, but we'll write the acceleration with the minus sign. So v as a function of time will become u minus gt. Displacement as a function of time will become ut minus half gt square, and v square will become u square minus 2gs. So particularly these two equations are important. And now if you look at the velocity versus time graph, you realize that it's basically like we discussed in the general situation. So velocity starts from the value plus u, but at some point of time the velocity becomes 0, and then at some point of time when it comes and hits the ground, that's the time capital T, the velocity will have some negative value. And also if you look at the displacement versus time graph, now in this sort of case I'm not worried about what happens after it hits the ground, whether it bounces up or it just sticks to the ground, or it even digs a hole and goes certain depth inside the ground. I'm not worried about that part. I'm just solving the motion up till the time it impacts the ground. So this will be the time when it impacts the ground, because the displacement will have become 0. Whereas exactly at half of that time, you see it will reach the maximum height. Okay, so this equation corresponds to this graph, like we've seen earlier. This equation corresponds to this graph, and by using these equations only we can find out all these things. We can find, so suppose we are given the value of initial velocity and we know the value of g. So we are given these things. So the value of u is known, the value of g is known. Then we can find the maximum height, the total time, and the impact speed for this. Okay, so just note this down quickly, and then we'll see from the three equations how we can develop the formula for these three things: the maximum height it travels to, the total time it takes for the ascent plus descent, to go up and come back to where it started from, and the impact speed with the ground. That is, when it comes back to the ground, what is the speed with which it hits the ground? See, Vedant, the point is now here that the sign of A depends on how we have taken the axis. It does not depend on whether the body is accelerating or decelerating. Acceleration or deceleration comes from the fact that whether V and A are in same direction or they are in opposite direction. So here I've taken y-axis upwards. So my acceleration will always be negative. But the difference is from 0 to highest point, U is velocity is positive and A is negative. Whereas from highest point back to the ground, the velocity is also negative, A is also negative. So it's again a case where they are in the same direction. Okay, so hope this point is clear.
So,
Yes.
so you wrote the given U and G, right? Like if U and G is given, so we could find HT and V impact.
Given numerical value of U and G, like suppose we are telling you that okay, you're throwing the object at 20 meters per second and take the value of G as 10 meters per second square. Then from that we can calculate in meters what is the height, in seconds what is the total time of this.
And so V impact also, right?
Okay, so let's see how to develop the formula for these three things: the total time, the maximum height, and the impact speed. Mostly that happens with practice, beta. Approximate values so quickly mostly happens with practice. The one or two tricks I use, like binomial approximation when necessary, but like when that happens, I will tell you like what trick I'm using for doing approximate calculations. Okay.
Yes, sir.
Okay, so let's see this. So you can see that first of all, at the highest point, instantaneous velocity will be 0 and the displacement will be equal to h. So from equation 3, this one, this equation here, put V is 0. So you get this maximum height is equal to U square by 2G. This is the formula for it. So for example, if U is equal to, let's say, 40 meters per second and G is equal to 10 meters per second square, then what is the maximum height? So we just use this formula. So you'll see that this will become 40 into 2, 80 meters. 80 meters will become the maximum height. Then the other thing is that at t equal to capital T, when it returns to the starting point, its displacement should be 0. So from equation 2, you can see that 0 is equal to ut minus half gt square. So from this we get the value of time as 2u by g. So in this case, be 8 seconds. Now one more interesting thing you can see from this only is that at the highest point, v is 0. Okay. So from equation 1, the time is u by g. So that is actually equal to capital T by 2. So it reaches maximum height at half of total time, capital T. To go up and come down, whatever is the time, it takes half of that to go up and therefore half of that to descend down. So the ascent and descent are symmetrical. That means suppose the total time, like in this example, was 8 seconds. That means for 4 seconds it will be ascending, and the next 4 seconds from 4 to 8 it will be descending. Always that symmetry occurs. That symmetry you can understand from the graph that I've drawn. You can understand from how I've shown from equation 1 over here. Always remember that it will reach the highest point exactly at the halfway time of the journey. Okay, and for impact speed, you can see it's very simple. You just put the value of capital T in equation 1. So at t equal to capital T, V's value will be the impact speed, or the impact velocity we'll see in this case, because it will come with sign. So Vi is equal to U minus Gt. So that is U minus G into 2U by G. So you see that the impact speed is negative of the initial speed. I mean, impact velocity is negative, so it impacts at same speed as the projection speed, that is the speed with which you have thrown it. So this is another important property or aspect of this kind of vertical motion or vertical projection from the ground. That symmetry, that whatever speed with which you throw the object up, it comes back to ground or it comes and impacts the ground at the same speed. And it takes this exactly half of the total time of the journey to go up for ascent and the remaining half of the time for the descent. So that symmetry is something important. The rest you can just see how you're basically using the same 3 fundamental equations that we've been discussing from the last lecture. That is uniformly accelerated motion along a straight line. Okay, so people, with this we conclude today's session. Okay, so be sure to revise kinematics in 1 dimension, what we discussed in lecture 1 and 2 very carefully. The part before this thing also, uniformly accelerated case, the part before that, how we use calculus, that part. And then of course, the 3 equations for uniformly accelerated motion and their application. Make sure you do this very carefully, so that should make sure that your kinematics problems will not be anything to worry about. Okay. Also do a revision of calculus because that's also coming in the major test. So that's it for today's session, people. Wish you all the best and thanks for
Sir.
joining.
Thank you, sir.
Thank you, sir. Bye.
So,
Yes, Laksh, you had some question?
sir, what you have written down there with blue pen?
Yeah, after Vi equal to minus u, it's that it impacts at the same speed as the projection speed u. But the Vi is minus u, that means speed same hai, but direction opposite ho gaya. Understood? Na?
Sir, that blue one at same speed up before that.
Impacts at the same speed. That word is impacts. Okay? It
Okay,
impacts
sir.
the ground.
Sir,
Yes.
sir, in that third point, the impact velocity is the velocity of the total journey, right?
It is the velocity at the end of the total journey. Like at the instant when it's finished the journey. It's just about to finish.
When it reaches a maximum height and when it falls, so that will give us this impact velocity.
Yes.
Okay, sir. And sir, for the total journey, we will use that normal formula, na? Matlab V is equal to U minus GT.
Yeah, we have used that second equation only, that S is equal to ut minus half at square minus half gt square. No? So from that only we got the time of the journey. The second equation we put S equal to 0.
Okay,
When it
sir.
completes the journey, it's back to where it started. S should be 0. So see, that's how we have derived the value of capital T. The second part is from equation 2. Put S as 0. Got it now?
Yes, sir. Yes, sir. Thank you, sir.
Thank you, sir. Bye, sir.
So, sir, the impact,
Sir,
sir, the, sir, excuse me, sir. So,
Yes, yes, Aman.
so the impact speed and the projection speed is equal. Is it applicable for all the the conditions then? This
It is
one.
applicable whenever the motion is under the action of gravity. Okay. But for example, if there is some other force along with gravity, like wind resistance, or air drag force or something, then it will not be applicable.
Okay, sir.
But when we say motion under gravity, the assumption is that there is no second or third force. There's only one force acting, which is the gravitational force. Okay?
Yes, sir. Okay, sir. Thank you, sir.
So unless the question says specifically that assume there is drag force or gives you some information about something other than gravity, you'll always assume in vertical motion, the motion is happening only because of gravity. Okay?
Yes, sir. Thank you so much.
Okay. Good night.